Let me first invite Dr. Arjun Datta from IISER Pune. He is a seismologist and he will tell us about the potential of such a facility for seismology.
Good afternoon, everyone. I'm Arjun Datta and it's a great privilege and honor to be here. Thank you for having me. As Professor Amol said, I'm going to talk about the potential for high precision, what I call high precision seismology in an underground science facility. So first of all, why seismology? What is seismology and why do we do it? Why is it important to do? There's a multitude of reasons, but I've picked out a few to explain why seismology is an interesting and important science. It's obviously used for earthquake monitoring. Without seismology, we wouldn't know where earthquakes are happening around the world and which ones are bigger than others and so on. It's also used to understand the processes that actually happen when an earthquake occurs. So an earthquake is a rupture somewhere inside the Earth's crust. What type of rupture actually happens? What kind of slip happens on what segment of which fault in any fault zone? For example, this figure is showing an image from a study following the Gorkha earthquake of 2015 in Nepal, which some of you might remember. It was a large earthquake. And this picture is showing their analysis on how the rupture propagated, and they were able to deduce the speed of the rupture and so on. So really understanding the fundamental processes behind earthquakes. And of course, there's implications of seismology for natural hazard assessment, not only from earthquakes, but also volcanoes, tsunamis, and therefore early warning systems can be built. It's also relevant for exploration for natural resources, oil and gas, minerals, and so on. And then not finally, but it's used for research in many fields, but also in plate tectonics, which is a buzzword that some of you may have heard of. This image is showing a subducting slab of lithosphere. I'm not sure if these words really make sense, but if you see this blue segment over here, that's showing a plate of lithosphere that's actually diving into the mantle down to about 600 kilometers of depth. So we are able to construct such images because of seismology. And finally, it's used to study Earth structure inside the Earth. So what do we know about the Earth? It has a crust, mantle, core, and then there's a lot more that we try to find out. For example, this is an image from a study that claimed to image the mantle plume beneath the Yellowstone National Park in the United States. So this is the red feature that you see is actually rising up all the way from the core mantle boundary at the bottom and going up to the surface. So this is supposed to be an image of the plume, or the Yellowstone plume. There are also global tomographic models. Here, this figure is showing 4 different models from left to right, and it's showing a spatial distribution of shear wave velocity at different depths inside the Earth. So that's 50 kilometers at the top, and this is 500 kilometers at the bottom. And what kind of structure do we see inside the Earth is shown in these images. Of course, 4 different models giving you 4 different pictures tells you how difficult it is to really say precisely about what the Earth looks like inside. So that's an overview of what seismology does, but how is it into the volume of the Earth, and they are refracted back up to the surface because of velocity gradient. So they're recorded elsewhere at some other location. So you have an earthquake, let's say over here, and you will record somewhere else. And then what you actually observe is the figures on the right are an example of that. These are called seismograms, and they're basically a record of ground motion. For example, these seismograms, they actually show waves that are used to study the inner core of the Earth. And this particular example shows that the inner core is anisotropic. So waves in one direction in the polar direction are faster than in the equatorial. So this is, in a nutshell, in a very simplified picture, what seismology does. Okay, so why am I talking about it in this session on an underground facility? A seismometer, which is the instrument that detects seismic waves, is conceptually very simple. It's just an instrument that measures ground motion relative to an inertial mass. So this is a cartoon that depicts that concept. So you could just put this on the surface and measure ground motion. So why are we talking about underground? Well, actually the largest seismometer deployments around the world are already underground. Not as deep as we are talking about in this session, but they are underground. There are surface deployments, but there are all the permanent networks around the world, seismometers to depths of at least a few meters, if not tens or hundreds of meters. So they are called vault installations, or the deeper ones are called borehole installations. And this is the schematic showing the idea. The actual sensor, which is the part that detects ground motion, is shown over here. That's the part that's underground. And then overground is the power supply and the communications and so on. And the idea behind burying the sensor is to avoid wind and rain and human activity and other activity, which is at the surface, because that produces noise. And this is an example. It's actually a photograph of a particular deployment in Calgary, in Canada. So you don't actually see the sensor, you only see the solar panels and the battery and so on. So most of it is few meters or tens of meters, but there have been scientific drill holes, and there have been many. These are a few that I've picked out, few well-known examples where they have actually deployed seismometers at a couple of kilometers depth. 1 to 2 or 3 kilometers depth. So why go underground? Part of it is intuitive, but not all of it necessarily. And first of all, what frequency range do we actually observe, or what frequency range of seismic waves do earthquakes actually produce? This is range from millihertz, or less than, or about 10 millihertz to about 10 hertz. That's roughly the range. And the first reason why you go underground is simply because the near surface, we are standing on the surface of the earth, the near surface, the part of the underground that's very close to the surface, is quite contaminating. It contaminates the signal. It's strongly attenuating, strongly heterogeneous or scattering, and most of the time we're interested in studying deeper structure even if it's the crust, it's several. This is just a few meters or tens of meters. So why not record the waves before they actually pass through this contaminating near surface medium? Of course, if you're interested in seismic hazard, then the near surface is important because it affects how these waves appear on the ground and how they cause damage and so on. But when as a seismologist, if you're trying to study the deeper earth, which is well below the near surface, then you simply want to avoid the near surface. And then actual background noise also reduces as you go inside the earth. Part of that is intuitive. I already said about wind and rain and human activity, the interaction of the oceans and the atmosphere with the solid earth that produces something called ocean microseisms. These things are well known, but actually all of these things only operate in the intermediate and high frequency band of seismic wave propagation, which roughly I would say is 0.1 hertz and above. Now this may sound like fairly low frequency to some of you depending on what field you're from, but in seismology 0.1 hertz and above is considered intermediate or high frequency. Below that is actually low frequency. So what about low frequencies? At low frequencies we have non-seismic noise, so to speak. Non-seismic in the sense that these are not seismic, or these are not ground motions that are being produced, but they are still noise in the sensor. And the most important of this non-seismic noise is so-called tilt noise, which is an apparent horizontal acceleration. A seismometer measures vertical as well as horizontal ground motions, and in the horizontal there's apparent accelerations that are produced because of which in turn are caused by pressure and temperature variations in the sensor. At the surface you have temperature pressure variations, but as you go down it becomes more stable, and the tilt noise reduces. And because of tilt noise, the horizontal component of the recordings at low frequencies is always more noisy. So at low frequency, you have this strong, there's also other things like magnetic field variations and so on, but this is the main one that I wanted to mention. Okay, so why am I talking about this? Why should we care? Fine, we have some noise. Why should we care about the low frequencies? That brings me to what we really want to do with an underground science facility, if we can get one. What are we going to do with it? So personally, my interest is in something called normal mode seismology. This is low frequency seismology. So I'm going to compare mid to high frequencies on the left hand side with low frequencies on the right hand side. In the intermediate to high frequency band, we have traveling waves, which, as I said before, they dive into the medium and then they come back up, they're refracted back up, or they propagate parallelly across the surface, surface waves or body waves, respectively. So these are traveling waves, but at low frequency, you have normal modes of the entire Earth. So these are vibrations of the whole Earth, and they're effectively standing wave patterns that are produced in the entire medium when you have a large earthquake because of globe circling surface waves and so on. And I'm showing two types. I'm showing two types of patterns over here. You'll notice that in the left one, the one with 53 minutes. By the way, that's the period of the oscillation. 53 minutes. That's how low frequency it is. So there's on the left there's a spheroidal, so-called spheroidal oscillation, and on the right it's so-called toroidal. And this is a bit of a technicality, but there's a reason why I'm showing it. So spheroidal modes are like this. They have a radial or a vertical component of motion, whereas toroidal modes or torsional modes have a shearing only. There's no vertical, there's no radial direction of motion, there's only a shear or a twisting motion, hence the name torsional. And because because there's no vertical, they are only observed on the horizontal component. So you remember what I said about the horizontal component being more noisy. On the observational side, traveling waves are seen like this through seismograms, as I said before. Normal modes are observed actually through the spectra of the seismograms. So you take a very long seismogram, several days long, you transform to the frequency domain, and then you can see these various peaks that correspond to the various eigenfrequencies of the Earth. And so you can really see a large number of modes if you have high quality data, which is the key. So why am I interested? Why should anyone be interested in normal mode seismology? There's a couple of very good reasons. Well, firstly, unlike traveling waves, they sample the entire Earth right down to the center or the inner core of the Earth. Secondly, they have a very interesting sensitivity to the density structure of the Earth as well because of their very long wavelengths. Traveling waves do not do that. If we want to learn about the density structure of the Earth, we can't use body waves or surface waves, but we can use normal modes. And lastly, they're not limited by the geographic distribution of earthquakes and stations, because traveling waves are limited by it because there's a certain path that they will follow, whereas normal modes, once they're set up, the entire Earth is moving. But they do come with their challenges, and the primary challenge is that only the very largest earthquakes can really excite these modes to the point that they can be observed, and that's because there's always background noise. So for these modes to be observed above that background noise, the earthquake simply has to be really large. And torsional modes are particularly hard to observe because they're only seen on the horizontal components, and as I said, the horizontal components are always noisy. And here's an example of what is actually done. The physicists will be familiar, of course, with the Zeeman effect in atomic physics, where spectral lines of a hydrogen atom are split. The Earth actually has something similar. The normal modes, here I'm showing vertical and horizontal component modes or spectra. But the interesting thing is if you could just focus on these red circled regions, you'll see that some of the peaks are split into 2 peaks or 3 peaks. So that's something called a splitting of multiplets, where the degeneracy of these modes is destroyed. And that's how one actually studies, that's how one uses normal modes to study Earth structure. Because it's the heterogeneous Earth structure that causes this splitting or this breakdown of degeneracy. So my point with this slide, I'll just take a few seconds, is that one really needs high quality data to perform an analysis like this. Firstly, you need to see the modes, and then you need to be able to see their splitting functions, and then calculate the structure. So it's extremely high quality data that's needed. And so what would be the benefits that an underground facility will provide? Well, firstly, it can give us high fidelity recordings of normal modes. And because of that, we may be able to use splitting function measurements from smaller earthquakes. One doesn't have to wait for very large earthquakes, which happen once in a few years, fortunately, to get the data. Smaller earthquakes can be used to get the observations that we want. And the other interesting thing is that density structure of the Earth can also be obtained from neutrino tomography, as the next speaker is going to tell you. And a USF will allow the very exciting possibility of jointly of combining these 2 types of observations, normal mode seismology and neutrino tomography. If you combine them, you could potentially get much better constraints on density structure than from either method alone. So in summary, I've told you that seismology sheds light on the processes that shape the Earth. A USF will facilitate very high quality observations of the kind that we are not able to make otherwise. And with these observations, potentially also with neutrino tomography, which may become a reality 1 or 2 decades down the line after the facility starts, one could get highly improved 3D density models of the Earth, which in turn can be used for a variety of scientific problems in Earth science. Thank you.
Thank you, Arjun.